Cherie Ho is currently a third-year PhD student in the Robotics Institute at the Carnegie Mellon University, advised by Professor Sebastian Schurer. She received her bachelor's degree in engineering from Harvard Med College in 2017. Her research interest is at the intersection of field robotics, control theory, and machine learning towards the goal of bringing robots to uncertain safety critical environments. Specifically, she develops robot learning and control algorithms that provide theoretical safety guarantees whilst deployed in the field. Cherie has published papers on Journal of Field Robotics, IROS, and the SEC. She is a recipient of the Crutcher Scholarship for a doctoral study. So that's welcome, Cherie, and we are ready for your talk.
Thank you for the intro. Very excited. Thank you for inviting me to give the talk. So please feel free to stop me at any time. A lot of these work are like in development, so I have my notebook ready to take down questions. So even if I can't answer them, I would want to find out how I could have answered them, and that would help my work in the future. So let me start the canonical question of if you can see my screen.
Not yet. Now we can.
Yes.
Okay. Can you see my presentation screen? Great.
Yes.
Also, I really appreciate that everyone has their face on. It makes this so much easier. So, cool. Yeah. So, hi everyone. I'm Cherie from CMU Robotics Institute. Thank you so much for inviting me to your lab meeting. And today I'll describe our work on safe collaborative robots in dynamic environments. So one interesting thing is I'm actually also from Air Lab, but from CMU. So that was very cool. We have different capsulizations. So, all right. Cool. So we're now living in a really exciting time in robotics, where autonomy is really rapidly innovating to meet the demands of society. So aerial autonomy in particular, being an Air Lab, has lately received a lot of attention with its potential to change point-to-point transportation, increase logistic efficiency with drone delivery, improve search and rescue, and even reinventing cinematography with never before seen angles of dynamic actors doing parkour, motorbiking, and everything. And these all under the hood require the vehicle to operate under varying environments under safety critical applications. So more recently, we've been seeing a huge push towards multi-robot autonomy to dramatically increase the productivity of our autonomous agents. For example, to dramatically reduce search and rescue time in the bottom right image, which is our lab's DARPA sub-T effort. It can also increase possible loads carried by drone delivery robots. I saw this from one of your lab mates' recent work. To scaling aerial transportation for mass use. So at the crux of all these dynamic applications are three key desired properties: safety, real-time computation, and high performance. These vehicles will need to work within close proximity to humans, such as in the cinematography application, navigate between buildings, above pedestrians, under high wind conditions, or fly in close formations to each other, which has unknown aerodynamic effects. And while doing so, need to actively reason around safety. Second, the vehicle will receive new information and must make these decisions in real time. And thirdly, vehicles need to make high quality decisions to avoid inefficiencies that may lead to mission failure. Later, we'll also see how these properties are at odds with each other, as I'm sure that we all have to optimize and hand tune sometimes. And these properties and their optimization becomes even more difficult to achieve when extending to multiple agents. So to ground this talk, I'll be using a motivating application that we're working on to generate millimeter level reconstruction of dynamic actors with autonomous flying cameras. This is a joint NSF-NRI project with University of Minnesota. We're mainly motivated because we find limited methods to accurately measure dynamic group activities in their natural habitat, with most methods reliant on GPS markers or within indoor environment. So we hope to break this technology out into the wild to bring Fly Optics Studio, where our system can take the grand vision is that our system can take a single autonomous capture of animals or humans in their natural habitat to later generate infinite post-hoc views. This will require many viewpoints while reasoning around natural obstacles and uncertainties. We're motivated by strong applications in biological tracking, where we are excited to better understand finite movements of wildlife animals, to entertainment, where we can post-generate infinite camera views in the editing stage, or to even computation as a scalable system to collect high-quality 3D data for data-driven models. So scaling it back as we take the first baby steps towards this project, we break the problem to 4 main parts: multi-actor tracking and forecasting, multi-robot viewpoint planning, safe planning under uncertainty, and then with the output of the footage for the high fidelity reconstruction. This is the first year of the project, and in this talk, I will focus on our work on multi-robot viewpoint planning and also safe planning under uncertainty. As we recall, the desired properties of our autonomous system is we hope to build an autonomous multi-robot system that exhibit safety, real-time computation, and high performance, while in dynamic environments where for the multi-robot viewpoint planning case, it is with a dynamic actor. And for the safe planning, we focus on the scope of varying external disturbances. So to address this general problem of safe collaborative robots in dynamic environments, I will present 2 works. First, a collaborative aerial camera coordination scheme for reconstruction of dynamic human amongst obstacles. Second, to ensure safety under these varying uncertainties that we see in our application, I'll introduce adaptive safety margins under time varying disturbances. These 2 works right now are separate. However, we hope to bring these 2 work together to achieve our vision later. So before diving into our work, I'd like to acknowledge all my collaborators and our lab, also called the Air Lab, to bring our ideas to fruition. All right, on to our first work on multi-robot viewpoint planning for 3D human reconstruction. So in this work, we address the question of multi-camera planning for best skeletal reconstruction of an actor amongst obstacle. And here we show that we can reconstruct dynamic actors, such as here below with a jogger. This is tested in one of our forest testing environments a month ago in heavy snow. We were also able to reconstruct people doing jumping jacks and also soccer, which I'll show some videos later. So towards this problem, we're inspired by works from several topics, spanning from static site reconstruction to active planning for aerial cinematographer. However, current work do not address the entirety of our dynamic human skeletal reconstruction in the wild problem. First, at the top left corner, there has been a wealth of work, especially in the active planning field, on reconstructing static sites, often using an information gain formulation to maximize coverage of complex geometries, for example, this building here. This problem, however, differs from our application, as the robots generally have a long time to scan an area, collecting many viewpoints. Whilst in our problem, the reconstruction surface changes at every time step, and we can only collect information at that instance. So moving towards active planning for dynamic agents. So towards specifically for human motion capture, we find some learning-based approaches that really interestingly explicitly optimizes for best viewpoints. However, they're mainly limited to obstacle-free environments, whereas we want to have these work in the wild. We built on our previous work that developed an autonomous aerial system that can detect, track, and follow targets amongst obstacles and avoid occlusions. However, the driving application of that is for aerial cinematography, where we're optimizing for an artistic cost. Most related to our work, I was very inspired by a multi-robot aerial motion capture system, where the drones are positioned in such a way to minimize the 3D actor position uncertainty while avoiding obstacles. However, it might not directly apply for our application as it plans for a very short horizon and does not avoid occlusions, which I will talk more about. So kind of breaking apart this geometric problem, why is it exactly hard to solve? We can think of a standard scenario where we have some drones tracking one dynamic target. The distinctive challenge of developing an autonomous reconstruction system for dynamic actors is the need to compute high quality simultaneous viewpoints amongst obstacles while staying safe. We break this challenge into 4 main factors that we later encode in our problem formulation. First, maintaining safety. This is the primary objective of our autonomous system, where the robots must stay safe from each other, from obstacles, and from the actor. Second, 3D reconstruction requires simultaneous viewpoints. We must therefore penalize possible occlusions, such as this tree, to maintain actor visibility for good reconstruction. Third, intuitively, post-estimation, especially learning-based 2D skeleton detector, such as the one we're using here, is most successful when the majority of the body is in view, likely because that is the majority of the training data distribution. We can see here much worse performance to the right when the tilt angle, which we define as the relative angle from the ground to the drone, where the detector constantly misidentifies the legs and the arms of the actor. So on the other hand, we see consistent skeleton detection when the tilt angle is low on the left. Therefore, we would like to maintain a low tilt angle. And then lastly, given a limited number of UAVs, we would like to maintain a relative yaw angles between UAVs to give the best information for reconstruction, where we need a good balance between good coverage and overlap. Coverage in order to represent most of the bodies, while overlap in order to maintain correspondence for alignment. For example, to the left, we have here where the baseline is too small, resulting in poor coverage of the reconstruction, and also at the same time, uncertain depth due to triangulation error. Whereas when the relative yaw angle is too wide, it does not provide enough correspondence for 3D reconstruction. And these we actually had to learn the hard way. We collected some field tests and then it did not work well for our reconstruction method. So this value is of course driven by the different reconstruction method. And I will talk more about that later. So encoding these 4 intuitions and challenges, we formulate a trajectory optimization problem to find a set of trajectories with minimal total cost. This is represented as a weighted set of cost functions that balance robot safety and motion smoothness against visual occlusions of the actor from obstacles. In addition, we introduce an objective J4, which is to encode the multi-camera collaboration formation that strives to keep it optimal for reconstruction over time. So to the right, we have some definitions where the ith UAV trajectory is represented as psi qi. And then what we're ultimately solving for is the set of trajectories, which is a big psi. And we are also given an actor trajectory psi a and a map, which is a voxel occupancy grid. So our key idea to balance all these objectives is to plan best formation path over a long time horizon using a two-stage approach. By reasoning over a long time horizon, we're able to generate good simultaneous viewpoints amongst obstacles and avoid myopic trajectories. And our two-stage approach allows us to dramatically reduce complexity so we can adapt very, very quickly to highly dynamic targets while providing smooth trajectories. So see here in our cartoon, we see the input to our planner, a map which we have the trees, an active forecast, which is the black dashed lines, and also the current UAV states. So first, we plan discrete viewpoints using a centralized formation planner on the lead drone. And then in each UAV, the discretized viewpoints is then optimized for a smooth trajectory that is later tracked by the vehicle.
Excuse me, just one simple question. Do you know the trajectory of the person?
Yeah, so we forecast the actual motion by using purely visual detection and then a Kalman filter based on their previous velocity.
Okay, but that's for a short time interval, right? Or do you plan for a long time interval?
So we plan for a 10-second horizon.
Okay.
We have shown that by just planning with respect to like path velocity has been quite successful. And one of our future work is actually better motion prediction, given contexts such as obstacles or like signs or things like that.
Do you also have some kind of a prior based on an activity type, like maybe this person is doing parkour and then 10 seconds is a pretty long time interval?
Yeah, that's a good idea. We have not explored prior based on activity. That is a great idea. One thing we have done before is we have different motion models. If it's a car, even though we're now doing human reconstruction and that one follows more of a car model. But I think the motion prediction right now is actually definitely a future work that we really want to dive into, because a good motion forecast can help our planning by a lot.
Do you assume that the map is known, or are you exploring that as the UAVs are exploring the environment, chasing the subject?
In this work, we assume this is a known map and a pre-mapped environment. We have shown in the past that we were able to explore with a LiDAR, and basically we model like unknown free space with a 0.5 as like the occupancy likelihood. And then like incrementally.
So you will not be able to at least at this point, handle dynamic obstacles that are not the subject. So for instance, if you had somebody going into an urban environment and you had crowds or cars and so on.
So our method is able to handle that. However, the system as of now, we removed the LiDAR from before, but it was also able to handle dynamic obstacles.
Okay, thank you.
Thank you. Yeah, so this is the occupancy grid, and in our formulation, it is static because I do assume a known map. In our previous work, this was something we progressively built, and we also have to calculate the sign distance value for later planning. Thank you. Okay. Okay, so just as a quick reminder, we propose a centralized, decentralized approach, and now I'm going to dive a bit deeper into these. Where okay, so here we first define some of the centralized cost functions. Again, this is planning the discrete viewpoints that we later optimize in a decentralized manner. So we plan formation trajectories using a state space parameterized by spherical coordinates, as you can see to the left, centered on the actor's position. To minimize the skeletal post-reconstruction error, the ideal camera formation that we found is should maximize the angular distance between the multiple cameras to minimize the triangulation error. And then, however, specifically for the case of 2 drones, we use pi over 2 as that gives us a good triangulation error. And note that this may be specific for our application where minimal overlap between the 2 camera views are needed because the skeletal pose, mainly the key points, is relatively sparse. However, for the dense reconstruction task, we're still experimenting with this. The relative yaw might actually need to be smaller to increase the correspondence for alignment. So to maintain safety, we must reason around the role of obstacles in the environment. So first, we transform the environment's occupancy grid into our time-dependent spherical domain, which you can see to the left, where for obstacle cost is the sum of the occupancy within a radius that we set, Rmax, of each UAV. And then most importantly, our work deals with occlusions as well. So in order to maintain target visibility at all times, we calculate the occlusion cost as a sum of the cost along a line between the UAV and the target. So intuitively, you can think of the UAV is here and the target is here. And we wish to minimize the penetration of that line to be inside the obstacles. So we want to push that out. And to the left, you can see a visualization of the occupancy and occlusion cost, where red is high cost. Note that you can see that the cost points behind the obstacle is also a high cost due to the occlusion cost. So to optimize over this formation, in this work, we fix the relative UAV angles to our desired angles, here 90 degrees, thus fulfilling our formation cost. Then this allows us to then simplify our problem to solving for the optimal yaw angle sequence over t time steps. The starting yaw is shown as the blue circle where the lead drone is. Then we define a state S with all possible formation yaw values, here being 8, over the interval -pi to pi. So we first build the cost map over that time horizon. Here, the time horizon is 3. So you might wonder why in the last 2 circles, there are circles that are red even though there are no obstacles. For example, you can see here at T1, in the bottom right corner, the bubble is red even though there's no obstacles there. This is because we account at the same time for the whole formation's obstacle and occlusion cost, where if the lead drone, which is currently in blue, swings to the bottom right corner of T1, drone 2 will be in collision. So that's the intuition behind it. Next, based on our cost, we calculate the cost to go map using backward induction, where we go back in time from T1 to T0 and to find the value function. We choose to use dynamic programming due to its simplicity and a small deterministic state space, where a single backward pass should yield optimal solution in little time. And to make the transitions between cells dynamically feasible for the vehicle, we only allow expansions to neighboring cells. So here we populate row T1 by evaluating each cell and summing its cost to its minimum cost next neighbor. We propagate to 0, where all values are 0, as each of the cell has a neighboring cell that has 0 cost. Finally, we build the full formation yaw sequence by selecting neighboring cells with the least cost to go at consecutive steps, starting at the formation initial yaw. So what we see here is the drone formation rotates anti-clockwise to avoid the obstacle while maintaining a good tilt angle. So after calculating the formation yaw sequence using the centralized planner, we optimize and smooth the individual UAV trajectories at a finer time discretization. So here, the second step is computed on each drone's local computer using a decentralized planning system, where the original waypoints were spaced at every 2 seconds over a 10-second horizon. Here we achieve a finer resolution of 0.5 seconds for local planning. This allows us to break the problem into 2 pieces, maintaining very fast replanning. So we test our approach with 2 DJI M210 drones with fully onboard perception to detect, track, and predict the actor forecast. All planning is done on board with the formation planning at 10 Hertz over a 10-second time horizon, and this operates in the lead drone. The decentralized planner runs on each drone at 5 Hertz and takes around 1 core. And the 2 drones both run their own ROS master and communicate to each other their optimized trajectory for inter-drone collision avoidance using DDS, so data distribution service. And here we see our approach coordinated 2 drones tracking an actor for reconstruction while avoiding a mount. Here's a more behind the scene look. First, we see the formation cost being populated with the resulting discretized formation plan in orange and blue. And in yellow is the smooth trajectory that is then passed to the lower level control for tracking. Here shows the time lapse of the previous trial, where as the formation rotates around the obstacle, it is able to maintain a low tilt angle. So to do the reconstruction, we use AlphaPose, which is a 2D skeletal key point estimator to estimate the joint locations. Then we fuse the measurements from the 2 drones with linear triangulation to estimate its 3D precision. And we see here our formation planning renders consistent skeletal reconstruction. And we compare this to a fixed formation that does not rotate. So to the bottom, we can see without formation planning, the robot, in order to avoid the obstacle, goes upwards at the right-hand side, reaching a tilt angle of around 60 degrees. And the skeletal key point detector therefore fails often for these footage, resulting in poor reconstruction. Finally, we showed a 3D reconstruction of a highly dynamic real-life actor playing soccer. Our system is able to keep up with abrupt motion changes and while maintaining optimal formation angle to provide good reconstruction. We're currently extending our aerial reconstruction system for a high fidelity view reconstruction. And this is ongoing work with my peer at University of Minnesota. Current methods largely assume parametric model, while our methods will be able to reconstruct details such as cloth wrinkles, facial expressions, and therefore drastically increasing realism and applicability. And here's a sneak peek of the integrated result. And my peer is now working on using multiple viewpoints to construct a full body high fidelity reconstruction. I invite you to visit her website to find out more about her very exciting work on using TikTok social media dance videos for better high fidelity reconstruction. So this is a beginning block of our Biopic studio, where our next milestone is moving towards multi-actor reconstruction. We're actively working on this in 3 main points. The first ongoing work is on onboard multi-actor detection and tracking, where we would like to also correspond and re-ID individual actors despite occlusions in order for better forecasting. We also want to see how we can best share the information between the multiple agents for better localization. Second, we're interested in the situation where a group of people might split amongst obstacles and seeing how our multi-agent, multi-drone framework should reconfigure its role to see if one should be a scouting whilst the other be more of a follower, to see how we can maintain the best reconstruction quality. Third, as we talked about before, we would like to improve on our actor motion prediction to use more context-driven based on the environmental factor. So concluding the first work, some of the key takeaways is maintaining good simultaneous viewpoints requires reasoning around obstacles over a long time horizon. And this is enabled by splitting up centralized and decentralized planning. However, this work does not fully address the dynamic environment problem, where we assume that the vehicle will stay reasonably within the planned trajectory, which might not be true under varying uncertainties. So the next work I'll present will be on how can we maintain safety under varying disturbances such as wind. And before we continue, is there any more questions on this first work? We can also come back to it as a whole later.
I have some questions, if nobody else has questions. First question is do you think about extending that for N robots? Like you have for 2, but your number of spots are around are limited, right?
Yes.
Do you think if you want to have 10 robots, how will you do it?
Yeah, that's a great question. So to 10 robots, one thing that we're trying out right now is also adding pitch into the planning framework. So similar to here, really fully using the discretization space of this in order to allow for 10 drones. However, one interesting problem I think would be by simplifying it to a ring of formations almost, we make the viewpoint selection much easier because we can sort of predict how the multi-view reconstruction would work. So by expanding the state space, I think we might need to use more data-driven methods to calculate what is the predicted reconstruction quality of different viewpoints at different heights.
I see, yeah. And have you seen some works where they use, instead of discretizing the circle, it works in the continuous space when kind of the robots push to each other?
You mean in the multi-robot planning space, or?
Yeah, for target tracking, when you want to track a target with multiple robots. I have seen multiple works in the continuous space. So this was the first one that I see discretizing the space.
Yes.
I was just curious if you took them into account or what is the advantage of your approach? Yeah,
so the main advantage of our approach is how quickly we can plan. One thing we have tested is we have a past work, which is by another one of my teammates, where he extended it up to, I think, 10 robots. And by taking this decentralized, centralized manner, it increases complexity linearly, which I'm not sure if the other continuous method would allow that. And we also see that the quality of the videos is still maintains at a very high quality. So that's our main consideration to decentralize to synthesis.
Okay. Okay. Thank you.
I had a question before we move on. We have time. So because you discretize the system, and even if you don't discretize, it seems like you're going to your formations will going to be constrained by obstacles. For instance, if you had the subject going through a narrow corridor, you might not be able to keep the 90-degree angle between them. So you might have to do like that is suggested a non-discrete version of this. Have you thought about things like this? I would assume this would happen when you would want to deploy this in urban environments or in forests where the density of obstacles is much higher and they have more complex shapes than the open field that were shown in the videos.
Yes, that is a huge consideration of ours right now. Ours is limited to, I think, some of the obstacle environments. However, we have tested our discretized approach in air systems, so like in urban environments, where I think that the main limitation on our end right now is the constraint on the formation angles. So I think by relaxing that formation angle constraint, which we have at like locked at 90 degrees, we are able to use our discretized planner in order to plan paths even in very cluttered environments.
I see. And the second question I had is somewhat closely related to this, is if you thought about applying this to things such as disaster scenarios, like whenever deploying in a fire, for instance, or inside a building where you would have to track, for instance, or monitor the people to give feedback to first responders. Is that something that you thought about? Is that interesting?
Yes, definitely. I think this aligns really well into one of our future work that we're considering is on adaptive multi-agent role reconfiguration, where I think for a search and rescue application, a lot of it is on kind of exploration and finding where is the most informative spot, then doing like then diving deep into it. So I think maybe right now our work would not directly apply. However, I think that one thing we're excited to do is to formulate this in terms of I think almost like an uncertainty minimization problem, and then try to search for survivors, and then while readjusting the agents to be at different heights for different resolution of information gathering. Then when it's like at the lower level for when it has identified actors to actually really give more information on, then I think it can switch to our current plan.
Yeah, see, I mean, this is very interesting because most search and rescue problems are about that searching, but actually in applications, once you find a person or a subject that is in need of rescue, you can't really immediately go there, and so you have to monitor up until rescuers can go there. So that might be interesting to explore.
Yeah, I agree. I think like technically it's like thinking about the different roles that the robot should play right now. Like you can almost think of it as the most low level, where it is tracking and monitoring to give high quality information. And then you might want to cascade up depending on the scenario. And I think that's a really exciting and very useful application.
Thank you.
Maybe we should just let Cherie to continue with her presentation and save some questions to the end.
Oh, sounds good. Yeah. I realized that it's at 45 minutes. Okay. So right now I'll introduce my second work, which is adaptive safety margins under time-varying disturbances. So safe real-time navigation is challenging because we need to work with uncertain vehicle dynamics, variable external disturbances such as wind, imperfect controllers, unforeseeable actuator, and perception uncertainties, all while reasoning around these with very low compute. And in this work, we focus on these 4 challenges, which represent a majority of the failure cases. Our work addresses this problem, these 4 challenges, by enabling safe real-time planning amongst varying disturbances. Here we see our quad rotor successfully avoiding an obstacle under wind by adapting its safety margins. And once it senses no wind, it adaptively decreases the small margin. So the key effect of these 4 challenges I talked about is tracking error, which is the vehicle's deviation from the planned path. You can see here the video, the quad rotor crashes despite a collision-free planned path, which is in blue. And in order to handle these tracking error, we often use some form of safety margins, which you can think of as obstacle inflation or tubes around trajectories. However, choosing these safety margins is difficult, especially when you're under disturbance which varies across a mission. So, for example, to the left, we have a narrow margin that works well for the first row, however, is not robust to unexpected disturbances at the second column. On the other hand, we find many prior work that computes worst case margins by assuming all experienced disturbance is always at a maximum level. However, this may be too conservative for most real world situations where most of the time the experienced disturbance is far less. In this work, we go beyond static offline margins to adapt pre-computed margins on the fly to better balance safety and performance. So a bit on the problem formulation. We formulate our problem as below, where given a reference trajectory, we find the most similar trajectory to follow for the vehicle to remain probabilistically safe under the current disturbance. So here, note you can see that the reference trajectory does not have to be obstacle-free. And let's consider 2 cases of the problem. Under high wind to the left and no wind to the right. And the dashed line is our reference trajectory. And we want to find a trajectory where intuitively, under the current disturbance, would minimize this red area. And you can see here with no wind, we expect the area to be smaller, therefore planning a closer trajectory. And formally, we find a trajectory that minimizes a similarity cost while under a dynamics, controller, and probabilistic safety constraint. And note that we consider disturbance and acceleration as we often model disturbance in drones in force. And our key insight to the problem is treating this as a surrogate problem of estimating the safety margins under the current disturbance, where we can write the constraints as a tube around a trajectory, which represents the set of likely vehicle positions similar to a reachable set defined by the margin radius. So to solve this overall planning problem, we split into 2 steps. An offline step to pre-compute margins for multiple disturbance ranges to solve the surrogate problem. And then online, we estimate the current disturbance information to query margins for safe real-time planning under time-varying disturbances. In the offline stage, we build a margin lookup table indexed by a motion primitive and a disturbance variance. And for each of the combination, we solved the circuit 2 problem to find a margin by simulating possible trajectories and fitting its margin. And the final lookup table of margins is then used during replanning for collision checking. So we choose to discretize the possible action space to a preset motion primitive library, which is commonly used for mobile robots. And by choosing a predefined set of trajectories, we avoid needing to generate these trajectories online. And it also reduces our trajectory search space, therefore just drastically reducing planning time. And also importantly for our application, allows for a fixed set of pre-computed margins. In this work, we use a library of constant linear velocity, angular velocity trajectories, defined by its linear and angular velocity and a time horizon. This method can extend to more dynamic trajectories. However, this will increase the size of your trajectory library, so there is a trade-off. Next, we define a range of disturbance variances that we would like to pre-compute for. There are many ways that we can represent the underlying model, where from one end, we can use a purely stochastic disturbance, where we sample at every time step from a normal distribution given a variance. Or on the other hand, we can use the worst case and set the disturbance constant at the largest possible disturbance. In this work, we use an underlying disturbance model that is described by variance and also a disturbance period, where we sample from a normal distribution and hold the disturbance fixed for that given disturbance period. The intuition here is that the same disturbance may affect the vehicle for a given duration, which is more representative of gust, but not necessarily over the whole horizon. So this gives us a middle ground between purely stochastic and worst case scenario. And with this model, an example disturbance standard deviation range is as below. Now with the motion primitive library and disturbance variance range set, for each combination of primitive and variance, we will compute a margin that describes our vehicle tracking error. So because of time, I will just quickly go through where we essentially forward simulate the trajectories given our disturbance model and our predicted vehicle model. And then this combination, this simulation for a specific primitive and variance goes through we then fit a margin to that set of possible trajectories. So it comes with 3 key stages. First, we split the primitive into segments. Then for each segment, we fit a normal distribution to the cross-track error and selecting a margin given by the desired confidence. And then in order to be conservative, we choose the maximum over all segments margin. Then we repeat this margin estimation process over each combination of primitive and variance to build a margin lookup table. So as expected on the picture to the right, we can see a gradual increase in margins radius, both when variance increases and when the turns become tighter. So now equipped with our margin lookup table, I'll describe how we use this for replanning given a reference trajectory and map. First, we estimate the current disturbance variance using online information. Then we query the column of margins corresponding to that variance. And within those primitives, we choose the collision-free primitive that has the least cost. The input to our replanning step is a map and a reference trajectory. So our first step online is to estimate the disturbance variance. We use a 9 degree of freedom quad rotor model and measure the disturbance based on the difference between actual and expected acceleration. Then the variance is a moving variance around 0 of the past disturbance. While simple, we note that the moving variance will cause a delay in our overall reaction time, and in the future, we hope to use a more predictive method. Then we choose the margins online given current variance. We start with a view of our pre-compute margins overlaid onto the primitives, where at the low variance, tubes are narrow, and at high variance, tubes are wide. And at the low variance, the smaller margins are used for collision checking, while the larger margins are chosen when variance is high. This is how the variance affect online planning, where for the same set of sense obstacles, all three primitives are available when variance is low, while when variance is high, only one is collision-free. Finally, bringing it all together, we pick the collision-free primitive with the lowest cost. So we call our planning objective, where we wish to find the most similar trajectory to a reference trajectory, which is now in orange. And then in black are our candidate trajectories parameterized by our motion primitive library. And we use our insight to replace most of our constraints to check if the primitive's tube is in free space. Then finally, within these green tubes, which are the free tubes, we pick the primitive that is closest to our orange reference trajectory. And the final selected trajectory is in blue. And here's back to the overview of our offline-online approach for real-time adaptation. So we first start with a simulated ablation analysis, where we independently test our key module, which is the lookup table, margin lookup table for online planning. We give our coordinator a straight reference trajectory through a pair of columns to travel under time-varying disturbance. A trial is successful if it reaches the end of the map without crashing. So we set up a map to clearly evaluate the effectiveness of the margin size to balance safety and performance, where when the margins are narrow, the reference trajectory is followed, hence cost is 0. While when the robot goes around the obstacle, the executed trajectory is far away and has a high similarity cost. So we compare our method to baseline static margins, which are the same computed margins, but locked at a static low variance, and another one at a high variance. So we see at a low turbulence intensity, the plot shows that in the lighter shaded region, the computed tubes, and in the solid line, the vehicle's actual odometry. And in this case, as expected, our wide static margin goes around the obstacle, which is overly conservative, while our adaptive margins goes through the pillars for a low cost trajectory. And at a high intensity gust, our vehicle with narrow margins crash due to high disturbance, while our adaptive margins adjust its margins online and therefore chooses to go around the pillar, thus staying safe. And to further test the robustness of our method, we use a larger map with 3 series of columns. And in blue, you can see an example of our adaptive margins of our system, where in the same mission chooses to go through the gap when the disturbance is low and around the obstacle when disturbance is high. We again compare our performance with the static margin methods under increasing level of turbulence, marked as L, M, and H, so low, medium, and high. And each data point in the safety trade-off curve is an average result over 10 trials in randomized disturbance sequences. So for the narrow static margins, it remains in the vertical axis at the right, where the performance is high, but it's not robust to high turbulence intensity, thus crashing in 30% of the trials. While for the wide static margins, as expected, it is very safe. However, because it chooses to go around the obstacles, even when the disturbance is minimal, therefore it is at a low performance regime. Our adaptive margins dynamically computes best margin given current disturbance, resulting in lower cost than the wide static margins while maintaining safety, getting us closer to the goal of being in the top rate of this chart. So with the simulated validation, let's repeat again our real-world result, where we test in the real world with a varying wind field to show if our adaptive margins do better balance safety and performance under time-varying disturbances. We use a custom quad rotor with a Intel RealSense for state estimation and a TX2 on board for planning. So to the right is an image of our test setup, where the quad rotor is given a straight line trajectory and must navigate to the goal, which is at the end, amongst the wind field from our fans in the blue box. As our baseline, we use a handcrafted margin tuned for the same course without wind. And here's again the video I showed earlier of our system adapting to wind. Our margins increase as it sensed wind successfully, avoiding the obstacle under disturbance. And once out of the wind field, the margins dynamically decreases. And in contrast, in red is the quad rotor with our hand-tuned static margin. Under the heavy wind, it leaves its margin and crashes. We note that likely due to the slight difference in height, the quad rotor with the static margin actually experienced less disturbance from the wind than our adaptive margin trial. And yet it still crashed, showing the robustness of our method to higher disturbance. So now stepping through the adaptive margin result, the red line on the right side plot shows the disturbance standard deviation that is used to look up the margins. And at A, we can see that it starts at a low disturbance. And at B, when it encounters wind and experiences a high disturbance, the margins dynamically increase in size to move the quad rotor away from danger. And finally, at C, we see that the vehicle successfully avoids the obstacle and decreases its margin as disturbance has lowered. So in the future, we lay out 2 key steps to bring us closer to addressing safe real-time planning under varying disturbances. First, our method currently relies on our underlying distribution in our Monte Carlo step to reflect the real world. While we show promising results, we hope to extend our framework to robust adaptive replanning, where instead of needing to define our own underlying disturbance model, we take the same idea in our framework and pre-compute margins for multiple worst case bounds. This also allows us to better handle disturbance bias where our current distribution remains zero-centric. Second, we want to address the issue of no solution being found when disturbance suddenly increase. For example, this can happen when our quad rotor uses a narrow static margin to go through a narrow hallway, and however suddenly experiences large aerodynamic effects. With that, all margins would increase such that no primitives are collision free. So however, staying still is not necessarily the safest option. So one thing I'm interested in thinking about is formulating our problem instead as a minimum risk problem to address this issue. And second, we also hope to incorporate more predictive disturbance modeling to turn our reactive safety framework to proactive safety. And then that summarizes my second work, where for safe high performance flight under varying disturbances, we need to adapt safety margins. And looking more forward in terms of the overall problem, I'm interested in seeing how can we maintain safety under hard to model system uncertainties, for example, communication and perception failures. And looking forward towards safe collaborative robots in dynamic environments, we have 3 main key steps. First is extending our adaptive safety margin work to our multi-drone reconstruction framework to have it better handle environmental uncertainties. I think some interesting questions that we have not looked into with our single agent framework is can we share any information to decrease the uncertainty and get higher performance? Next, we're interested in incorporating perception uncertainties and communication failure by looking at common failure cases and deriving appropriate safety margins. However, this might be challenging because the perception uncertainty may fail under traditional Gaussian models. And lastly, we want to move from reactive safety to a more introspective paradigm, where instead of hand defining all these common failure cases, we want to see if our drone can predict their performance before it explores an area. For example, is there a safety curriculum we can learn in simulation to have it not go through really narrow hallways where it is very likely that there is a high aerodynamic effect? And seeing if there's a way to predict where uncertainties will be for more long-term safety. Thank you. That concludes my talk, where I talked a bit about our two works. And here is my list of collaborators again. Thank you.
Thank you, Cherie. I have a question.
Yep.
So I'm of course thinking about Skydio and Frank Deller's company, and I'm wondering if you know enough about what goes on behind the scenes with the Skydio controller to say whether you can leverage some of that or what its shortcomings are. And for example, one of the things I thought about was for that example in the lab where you had the fans blowing and your drone adaptively managed its its guard region. If you had a Skydio in your lab and you made it do the same thing, do you know what would happen?
That's a good question. I feel that from what I remember, I think they do have someone that is extremely, like his PhD thesis is on wind modeling and rejection. So I would guess they might have a good handle, at least for outdoor wind gust. But I'm not sure about indoors. And one thing that we noticed with the Skydio drone is amazing technology. And one thing we really differentiate is on the long time horizon planning, where as we see some videos, we can see, I think like there's a really cool video of a biker going through rows of trees. However, the drone, because we think that their horizon is more at like 2 to 3 seconds because they're solving for the whole model predictive control framework. Mm-hmm. So we see that our drone would probably like go through the trees because it also reason around occlusions. So we think that we can actually get better performance than that. But super exciting work from them. It's super awesome to see.
Cool, thank you.
Hi, Cherie. Thank you for your presentation. I think it was really great. I do have a question, and I'm not sure if I understand it correctly, but the way you measure the disturbance is by, you have your acceleration dynamics and you compare with the one you expected, and the difference will give you the disturbance, right?
Yes.
So my question is, there is any way to like predict or look ahead on this disturbance? Since I was thinking maybe if you're planning to go in for a corridor and you consider wind as the disturbance, maybe the obstacle might eliminate or dissipate this disturbance. So your tube might adapt to that, or?
Yes, definitely. I think one of the future work is making this more predictive. So let's see if I understand your question correctly. I think one thing that you're suggesting is also like maybe including in the disturbance prediction, maybe the environment of the robot. One concrete example can be a robot can choose between going through a narrow hallway and the outdoors, where a narrow hallway we see is actually has a lot of aerodynamic effects. Whereas like outdoors, generally, unless there's high wind gust, it's actually safer to go. So by including that future environment state into the planning, I think it'd be really exciting to see like it choosing to go in around the outdoors instead of going through the hallway.
Yep, thank you.
And I think a way to do that I was thinking about is maybe just like installing 8 of these really cheap LiDAR sensors almost. Not LiDAR sensors, but like just laser range sensors, and then seeing what the range, what the minimum distance to a obstacle is, and then use that to model in a bunch of different environments how well the aerodynamic effects work. And then you can then use that as a model, which is queried based on distance to obstacle for later.
Hi, I have a simple question, and hi, Cherie, it's a nice talk. And my question is for the safety, and if there's a very narrow gap and the flight has to change its pose to pass it, like because normal stable pose cannot pass a narrow gap, but so it has to change its pose. And there's a little disturbance in the narrow gap. And so I'm wondering if you can design an adaptive margin for different pose to pass different space. How's that question?
Interesting. I wonder if, are you talking in terms of like aerial robots, and by pose, do you mean rotation?
No, like they can be like that to have a very narrow gap, and there's a little disturbance in the gap, but you can make your safe margin to be more adaptive to the pose, to its own pose.
Yes, so that's actually, I think that would be really cool to see like how well it works with, the crux of my method is based on these motion primitives, and you can define, in order to include what you're saying, we can then define these very highly dynamic pose, I think, where we take very aggressive trajectories. And I think that can be a really exciting experiment. And I think our framework would allow for that.
Okay, yeah, thank you.
So, Cherie, can we go back to page 68?
Yep. Yep.
Here we go. As shown here, you are building up tubes adaptively, but those disturbances can be directional, right? But the radius of tube are always, it's not, right? This is always the same. So what do you think of that? Because if you can adapt the, the radius of the tube to the direction of disturbances, then you can probably generate more feasible passes.
Yes, definitely. This is a simplifying assumption that I made to keep the problem simple. And I would answer your questions in 2 ways. I think first, one easier way to do it would be to extend our margin lookup table to having more dimensions to allow for different dimension, like X, Y, and Z disturbance. That can be one, I think, easy way to increase the feasibility of our trajectories. Second, I think would be a more long-term would be, one second, would be actually lumping. I'm pretty excited to see how well this can lump into a more adaptive controller. So there's some really exciting work that I was talking to with UIUC, where they also add this to an adaptive controller. So that can itself already handle a lot of the major disturbances, whilst our dynamic tube can really address the transient nature of the disturbance. So I think this would be more longer term, but I think in order to increase the feasibility, this is what I will do by adding a adaptive controller in a robust manner.
That sounds good. My second question is regarding the offline simulation. So in offline, you are doing simulations, right? If I'm
Yes.
But if you are doing simulation, then there might be a reality gap between the simulator and the real environment. So do you see any problems there?
Yeah, so a key assumption of our margin estimation method is that it's twofold almost. So whatever we're experiencing in the real world, that estimated variance plugged into our simulated model, and like that sim to real gap is low. We do see this in the real world. However, I think what I want to do is to test this in more extreme scenarios, like beyond just wind, and to really quantify how big the sim to real gap is. And I think one way to even, I think one way to minimize the sim to real gap would be to actually take this robust adaptive replanning approach, where instead of modeling the disturbance, we pre-computed it for multiple worst case disturbances. So we are always conservative, but at different levels. And I think that will be the direction for the future, because it removes a lot of the hand definition and increases trust, I think.
Thank you. My last question is regarding to the first part. As you said, your method works best when the object or the subject stays reasonably close to the planned trajectory. But you also mentioned in the soccer example that your method adapted well to the dynamic changes. So I don't know which page is that. Yeah, probably this one. Yeah. Yes. So
sorry, when did I say the static thing?
Excuse me.
Sorry, when did I say about when my method works the best? I don't recall that.
Oh, I think in the last of your talk of the first part.
Yes.
Right.
So it's two separate things. We are able to really track highly dynamic actors. We were able to actually track cars that were 30 kilometers per hour. I'm not sure what that is in miles per hour. But then the second problem that I bring up here is that our vehicle stays reasonably well with the planned trajectory. So this might not be in really dynamic situation where there's really high wind, where there's actuator failures. The tracking error might cause these to fail this assumption. However, the highly dynamic actor is a different type of trajectory.
So during that highly dynamic event, your drones will stay relatively stable in the place, or it will just follow the.
Oh yeah, I see.
Actor.
It will follow the actor, like in the formation. What I meant by this limitation in particular is, even though it plans like the trajectories, if there's a really high wind, even though the planned trajectory is going this way, the wind might push it to the left.
Oh, okay.
So that's actually the error I talked about.
I see. Thank you.
Yeah.
Hi, Jeremy. I have a question about also about the reality gap problem.
Yep.
Pretty close to, it's pretty related to the problem by a second problem of Jingda. So during the simulation, you are using basically using the simulation to generate the tubes of different sizes based on different variances. Is that correct?
Yes.
Right. So in this case, we want to make sure that the model we use of the UAVs are as close as the reality. However, it's not always possible to get 100% accuracy on the models. So my question is, what are the some of the key criteria you want to make sure they are as close as possible in the simulation and the reality?
Yeah, that's a great question. So how I can talk through how I did my checks. First, as you talked about, I wanted my vehicle, the original vehicle model, not even the disturbance model, to be as similar as I can to the robot model. So for this, I did pick a simplified model. And then mainly I looked at, let me just pull up the 90UF.
Yes.
Sorry, one second. So I did use the simplified quad rotor model. It does have rotation based on desired attitude and thrust. And I did my best to fit first order road dynamics and pitch dynamics to this. Then secondly, on the disturbance model, let me just pull this up.
All right.
The disturbance model, I did take, especially for the simulation, I just took some, I guess you can call it training data. And then I evaluated what is the frequency of that. And then that's how I used to determine the disturbance period. And I felt that it lined up pretty well. However, I do think that, I think in the future, what I would like to do more is to rely less on disturbance models and be more model free about it. Because right now the disturbance is already trying to account for the model mismatch. And in order to do that, that's why I would like to pitch going towards adaptive robust planning, where instead of defining these models, we use like worst case disturbances, and you can just query them by maybe an overly conservative multiplier by the current disturbance. I think that would be a less model-based way for me to do this.
Got it. Thank you.
So are there more questions? If not, let's thank Cherie again for her very informative and interesting talk.
Thank you.
Thank you so much for the nice presentation. And thank you for coming to our lab.